It has you on it.
Is there a red light?
Uh, not that I can see.
Okay, that's not good. Ricardo, can you see something? I just want to make sure. There should be a red light. Or there should be something that says it's recording.
It's counting seconds.
Okay, okay, that's good. Will it work? I don't know. I don't know. Okay, so the example that we're going to start with is SATs. Okay? Okay, we know SAT scores are normally distributed. We know this. Are normally distributed with a mean of 500 and a standard deviation of 100. It's called a standardized score. So regardless of what your score is, it's sort of converted to this situation to make it really easy to understand where you are and all that kind of stuff. So the question is, if a person is selected at random, and again, not you individually, just a score is selected at random, okay? I want to find the probability that a score is less than 600. We're talking about one test. Okay, so you took an SAT, you know, what's the probability that somebody scores less than 600? So of all the people that took the SAT, I mean, first of all, is it going to be more than half or less than half? What do you think? Sorry? No one wants to commit. This is not something that requires any intelligence. I'm taking a score that's way above average and asking what's the chance somebody scored below a score that's way above average. Is that more than half the group or less than half the group? Taking a score that's way above average and asking what's the probability somebody scored less than that. Okay, let's back up. What's the probability somebody scored less than average? Exactly 0.5. So what's the probability somebody scored less than a really high score? More than 0.5 or less than 0.5? Come on, guys, this is not hard. If you're struggling with this answer, that's a really bad sign for the rest of the day. Taking a really high score and saying, what's the probability you scored? What's the probability you scored below the highest score? That's probably a really high probability. Okay, that's not something that requires thought or calculation, just look at the numbers. I'm asking above average and below. Now, we would like to calculate this probability exactly. Well, I can't look up 600 in the z-table now, can I? So what I need to do is convert this to a z-score. Now, how do we get a z-score? It's always score minus mean over standard deviation if it's a population. It's score minus mean over standard deviation this way if it's a sample. Well, SATs are a population. That's not a sample. It's every single person in the United States who took the SAT. So that's why we use mu and sigma in this case. So that's 500. That's 100. So what's the z in this case? I said a score of 600 minus a score of 500 over a standard deviation of 100. That makes it kind of easy. So what is it? It's exactly 1. Now, to look it up in a table, what number should I use? Because there's a lot of things that start with a 1. What do you think? You did this last day, remember? Probably some decimals. So what should I use? 1.00. 1.00, because there's actually, here's 1.0, there's 1.00, 1.01, 1.02, oh, okay, there's a lot of things that start with a 1, so I want 1.00 because I want to look at the right place. So the question that I'm asking here, by the way, like last day I said, always draw the picture to make sure you know which side you're on. That just makes life easier. So the question is, and here's how we write it. What is the probability that a score is bigger than 600? but I can't look up 600 in the Z table. So we said that is equal to the probability that Z is greater than 1 point, I'm sorry, I said not greater than, sorry, less than, sorry. We just did that. That's equal to the probability that Z is less than 1.00. Can we easily look up this one? Yes. Is there any calculation required to look this up? No. But we had to take this is what's called a raw score. We had to take the score and convert it to a Z-score so we know what to look up. Because I don't think I'm going to see the number 600 anywhere on here. I think I'm pretty much -3 to +3 is most of the results. So look at your tables. I've got it up here, but your tables will be easier to read. What is the probability of being less than, I mean, look at that picture. That's exactly what we have. Less than 1.00. What's the number?
8413.
8413. So in English, somebody took the SAT. How many people score below 600? About 84% of everybody who took the test. So is 600 considered a high score? Well, put it another way. How many people are going to score above 600? About what percent?
0.16?
Yeah, well, not 0.16%, about 16%. So the probability of about 0.16. So is 600 a high score? Yeah. But the calculation is only to convert the score to a Z-score, and we know that. In fact, that was the most common question on your first exam, was converting scores to Z-scores. That question happened more than any other question, so most of you had a pretty easy time with that. So in the situation of something like an SAT, right? Everybody knows their score if they took an SAT, but what does that score actually mean? How is it reflected? So let's do another one. All right? You're going to grab a score at random. Find the probability a score is, now, what would you say is a really high score? I think 700 is a really high score. I mean, everybody knows somebody who said they got 800. Everybody does know somebody. And the funny thing is, the few people I've met that said they scored 800 are some of the dumbest people I've ever met in my entire life, so I know they were lying, or they cheated. Because you can't score that high and not have a lick of common sense, or I know one of them, he still doesn't have his driver's license because he can't pass the driving test. But he swears up and down he got perfect scores on the SAT. Yet he never went to college. So, you know, you can always challenge people when they say things. What is let's say 700. Find the probability a score is above 700. 700 is a pretty darn good score. But what does it exactly mean? Okay, so the question is, in words, what is it, the probability to score above 700? Mathy-wise, it is, what is the probability your score is above 700? So we need to convert that to a Z-score. Now, formally, what I just did, I converted it to the Z-score off to the side so that I could say this probability is equal to this probability, right? That's pretty seamless. There is a way to do that in one step. Most of the textbooks will write it like this. This is equal to the probability that Z is greater than 700 minus 500 over 100, because that's the calculation I would have done off to the side. But I can actually write it in the middle of the statement. It's not Z equals. Oh, no. It has to be an inequality. Remember, in the table, you're finding area. Strangely enough, if you have a situation like this and you're asking what's the area above or below or between, if you ask for one individual outcome, the probability is actually 0. Because you're asking literally the area of a line segment, because you're only doing one score. So you never ask this question with an equals. If I'm rolling the dice or flipping a coin, that type of experiment I can say equals. But in this type of experiment, this is called a continuous distribution, like human heights and things like that. So we always do things as inequalities. So what Z-score would this be? So we'll look up, so 2.00, but now my picture is this. Does everybody agree? I'm looking at the right side, the right tail. Is that the number I'm going to see in the tables? What number do I see in the tables? The left. So how do we do this? Sorry, I keep having to go back and forth because I don't want to erase this. So we just said what we're looking for is the probability that z is bigger than 2.00, which is equal to which is equal to 1 minus what? The probability that z is less than. And that's the number we have to look up. Remember, the numbers are always to the left. It's always the less thans. So 2.00, what number is associated with that? 9772. And what does this give me if I take 1 minus that? 0.228. Would you say that's a pretty small probability?
Yes.
So in English, because we speak in percentages, we don't do math in percentages. Regardless of what anybody ever told you, you can't do math in percentages because you'll always be off by a factor of 100. You have to change percentages to decimals. Right? 50% is 0.5, it's not 50. In English, you'd say about 2% of the people score above 700. So is 700 considered, pretty rare? It's not impossible, but you'd say, yeah, only about 2% of the people are going to score above 700 on a particular one. So that's considered really a high score. But the nice thing is, I'm using SATs because SATs have probably the friendliest numbers you could ever have as a problem, because you're always going to have really nice numbers. But if you wanted to find out what's the probability of being in this range, okay, that's very important. So now, let's suppose, okay, at four-year schools, when you're applying, okay, we talked about this before. Now, I don't want to take like the Stanfords of the world, not the most elite. You got to be a high school valedictorian to be, even considered. But let's say we're just going to take any four-year school, and you want to go to that school. Okay, you are graded, you are scored your application. Now, let's say you're doing it right out of high school. Well, we talked about this last week. If you're applying, you have a high school GPA. That's important. Is that everything? You might have test scores, SATs, ACTs, things like that. So is that everything now? What if you were student body president? Do you think that would matter? Do you think, what if you volunteered in a lab somewhere? You got lucky enough to get some lab work in. These are all things that really add to your resume when you're applying. Let's suppose that you're applying and you're applying academically, but you also played sports and maybe you were team captain. Do you think that could matter? Yeah, again, leadership, things like that. So what happens typically is a lot of schools will say there's a bottom line of you must score at least this high on your GPA, or you must score at least this high on your SAT. Okay, because they have a line in the sand. They really don't want you dipping below. Do you know why they don't want you dipping below, like in those two areas? It's kind of a common sense thing. Why would they give you a line in the sand for GPA or SAT that they don't want you to go below at that whatever school they're talking about? Do you think it makes them look bad? Well, probably more makes you look bad. In other words, if they're setting the bar here and you're down here, are you going to be ready when you go to that school? Are you going to be ready to sit in a class and do well if you're below the standard that everybody else met? Probably not. Now, this is one of these areas, there's a lot of wiggle room. So a school will say you've got to score above a certain level. Now, GPA, that's easy. Most schools have a real clear line in the sand. Maybe it's 3.0, or maybe it's 2.5, or something like that. And an SAT, or it might be a combination. But let's just say that now the school's going back and looking at their applicants and saying, we noticed that our applicants were all between here and here. Okay? So now the question, I'm going to do a betweener, because we know that was the one that was a little bit more work. And again, I'm going to stick with SATs for now. So now they're noticing that their applicants at this particular school, whatever it was, that the applications, or the applicants, were between, let's say, 450 and 650. And we'll just say in the math score. They were between 450 and 650. So, what is the probability somebody is in that range? In other words, we're going to reflect the entire society. What percentage of society is actually, applying to that score? Is it the top 1%? Is it the middle? I don't know. So the question is, what is the probability that 450 is less than my score is less than 650? Right? Always smaller or bigger. Always in that order. So I'll need to convert both of these to z-scores. Because of these numbers, you could literally convert these in your head, but in general, you're probably going to need a calculator. So if I write it the way I did before, we'd say it like this. 450 minus 500 over 100 is my z-score. 650 minus 500 over 100 is the other end z-score. Okay? So what does that give us? And I'm going to do it on this board because I want a picture. I'm a big fan of drawing the picture every time, just to make sure I've interpreted the question correctly. All right? If that's 500, then I'm asking between 450 and maybe 650. It's probably something like this. Okay? 450 is below, 650 is well above. Now, I don't know what the answer is, but does it seem reasonable? It's probably close to a half. It's not going to be 0.999, it's not going to be 0.001. I mean, you're going by the accuracy of my drawing, but would you say it's probably close to a half is reasonable? So if I got an answer that was a million miles from a half, I would be a little suspicious. What happens if I get an answer that's greater than 1? Can you get an answer greater than 1? You're asking a probability question. No, you can't get an answer greater than 1. What if I get a negative number? There's two answers that you can't get. I just told them both. You can't be bigger than 1, and you can't have negative because probability is always between what and what? What two numbers is probability always between? 0 and 1. Yeah. So this is one where we had to look up two numbers. The only way I could get bigger than 1 is if I inadvertently add the two instead of subtract them. How could I ever get a negative number? Yeah, I subtract them in the wrong order. Does that happen? Yeah, I see people do that all the time. Nobody intends to make a mistake, but those are the two mistakes that are the most common. That I have my numbers, I just did the wrong thing with them. So do you remember how this works? I take the bigger one, and I subtract the smaller one, and that gives me the area between. So, first of all, we need to convert those to z-scores. So what's the first z-score?
0.6915.
No, z-score. Z-score.
Oh. 0.50.
Negative 0.5. Ooh, that's important, isn't it? Yeah, negative 0.50, and what's the second z-score?
1.5.
1.50. So now, what order do I subtract? It's going to be the probability of the bigger one. Oops. It's always the same way. It's the probability of the bigger one minus the probability of the smaller one. Now, that's what I'm going to look up. This calculation was not difficult. Converting these to z-scores was fairly simple, but I have to be able to subtract in the correct order, and I actually have to subtract. So what is the probability of a z-score being smaller than 1.50? 9332. What's the probability? Oh, I don't have it on this screen, so let me move. You guys all have your tables in front of you. Let me move to the next screen. What's the probability that z is smaller than negative 0.50? 0.3085. And what is the answer to that question?
6247.
Say 6.
6247.
6247. It's not a half, but it's not outrageously different. So I'm feeling pretty good. It's positive. That's great. It's not. It didn't exceed 1. Does everyone realize if I inadvertently added these two, I would have exceeded 1. If I had subtracted in the wrong order, I would have got a negative. And those are two things we can't have, but it's the easiest error check in the world because you know you can't exceed 1 and you can't be negative, so you go, okay, something went wrong if that happens. I just fix it easily enough. Are the calculations difficult? Not at all. But what you're doing, this is real life. Last day, all we did was, how do you look up numbers in a table? We had no use for it. We just said, this is how you look up a number. Now today I'm giving you situations and saying, what's the probability of this situation? I have to convert the situation, right? I have to convert it to something I can look up. But that's actually always short and sweet and simple. SATs are my favorite example to start with because the numbers always come out so nice. Why? Because your standard deviation being 100 means all your numbers are going to be beautiful every time. So now, I have a school, and let's say at our school, we only want to accept, this is a problem we looked at last day, in a sense. We only want to accept the top 10%, okay, of SATs. We're only going to accept the top 10% of SATs. Okay, great. So do we wait for all of the SATs to come in and then rank them and then count them? And that would be really inefficient. Wouldn't it be easier if I just knew what score to look at? So if you scored above that, you're in. If you scored below that, you're not in. That would make it a lot easier, wouldn't it? So what would the score have to be in the top 10%? This is not a trivial question. But we looked at this last day. We figured out a way to do this. Here's the question. And by the way, it may not be that I accept the top 10%. It may be that's your minimum score to apply. Interestingly enough, UC San Diego has a minimum GPA to apply. Does that mean you're in if you have that GPA? No, it means they don't look at your application if you're below that GPA. San Diego State has a minimum GPA that's significantly lower than the UCSD minimum GPA. But because San Diego State has so many more applicants, I don't know how many more, but I know it's more than 10 times as many. The minimum acceptance at San Diego State is above the minimum acceptance at UCSD. It's totally backward, but it's because of the sheer number. But they did it with GPA. We're going to do this with SATs. So I'm going to set the line in the sand saying this is the lowest the lowest SAT we will allow for an applicant because we only want to consider the top 10%. But if we have a lot of applicants, will all of them get in? I mean, think about it. If only people who can apply do, you know what the minimum qualifications are, you met them, so you apply. Does that mean you're going to get in? No. It means you will be considered, but it depends how many other people apply. If more people apply than they have space for, then people aren't getting in. It's that simple. So if you're applying and you didn't get in, it wasn't because you weren't good enough, it was because there were people that were better who also were applying and met the minimum. But we want to establish what is the minimum criteria if we said we're only going to consider the top 10% of SATs. So the picture would look like this. I only want these folks here. Okay? But I can't find that z-score in the table, so I want the z-score that corresponds to everything else, which would be what? 0.9. And technically, because the probabilities are 4 decimal places, so the question is, what z-score would this have to be that 90% of the people are below it? Okay, so what are you going to do? Oh, let me go back to the other table. We did this problem last day, just so in case you forgot. Oops. Look at the probabilities in your table. What is the probability that is the closest to 0.9000? I think we found it. I think it was right here. And what was that? What was the closest one to 9000? 8997? Was that the one we found that was closest? Yeah. So what z-score corresponds to that probability?
1.28.
1.28. So if I asked you the probability that a z-score was less than 1.28, in the table it's 8997, which is basically 90%. So the first thing is, we're going to set our minimum standards for applications. Your z-score needs to be at least what? 1.28. That's all well and good, but do you think a high school kid taking the SAT understands what his z-score is, or hers? Do they even know that that's what it is? No, we all agree 1.28 is the minimum z-score we would need to apply. So what score would that be? Oh, we're working backwards. What score would that be? I don't know. If z-score is score minus the mean over the standard deviation, then what's the score? Well, let's start by multiplying both sides by standard deviation. Then that would mean that x is mu plus sigma z. This is always true, by the way. I'm just working backwards to solve for x. Do we know all these numbers? Yeah. What is it in this case? 500 plus 100, and what's the magic z? 1.28. So rather than trial and error, just solve for x directly using algebra. And what score would that be? Use your calculator. Or do it in your head, because it's 100 times 1.28. So what would that be?
128. Is it 128?
Plus 500.
Oh,
So how about 628? A score of 628 would be a z-score of 1.28, which would put you in the top 10%. How do you know? Because 90% is to the left. So if we said, all right, we only want to consider, we're an elite institution. We only want to consider the top 10% of the applicants. Or not top 10% of the applicants, the top 10% of high school students. Whether you apply or not, we're only going to consider the top 10%. And then that would be the line in the sand. That's how it's done in real life. I gave you an example last week. I had a friend apply for the fire department in San Diego County, and he said there were thousands of applicants. He was very surprised. Okay? And they gave them a test. And what they did was, they did exactly this. On any type of test of this nature, it's generally a standardized test. They make it like an SAT. That it's scaled so they can get this normal distribution. And it was exactly the same thing. You had to score at least a 1.28 z-score to make it to the next round. Because that was the line in the sand. 10% of the scores, okay, 1.28. Isn't that interesting? That's actually a very common thing in real life. Now, does that mean you get the job if you're in the top 10%? No, it means you made it to the next round. Now it's simply a numbers game, right? If there's 100 positions, but there's still 1,000 qualified applicants, a lot of people aren't getting in. What if there's 100 positions, but there's only maybe 110 qualified applicants? Well, now they have a great chance of getting in. So that's a numbers game at that point. You're good enough to apply to the school that you applied to. They will consider you. But remember, applications are generally scored and ranked, as we said, and if they're only going to accept a certain number of people, and you don't make that cut, you won't get in. Now, what's interesting, has anyone here ever applied to a four-year university and either got accepted or rejected, but you've actually applied? Maybe you've been there before. What school?
SDSU.
Did you get in or not get in?
I didn't get in.
Did they send you a letter? Or did you just find out you didn't get in?
Yeah, I didn't get in. They sent me a letter because I didn't make contact for success.
The thing is, if they send you a letter, you know what that usually means? I know people that have gotten the letter. My daughter got a letter. She applied to Stanford and got a letter. The letter said you didn't get in, thank you for your application, the usual stuff, and actually said had you applied last year, you would have got in. But this year's acceptance was much higher than last year's, and you didn't get in. They actually explained to her. I've had San Diego State students applied. They got the letter that said basically, thank you for applying, blah, 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 blah. Basically, they're saying you were good enough to get in, but the numbers were against you this year. That's literally what they're telling you when you get the letter. A lot of times we find out we didn't get in, you found out. You make some phone calls, you didn't get in. But they don't contact you. You know why they don't always contact you? You know how many people they'd have to contact if they contacted everybody who didn't get in? I mean, San Diego State is probably in the hundreds of thousands. I mean, so I always tell me, if you got the letter, that means you were good. But were you good enough? Well, you didn't get in. So, in other words, here's how many people applied. Here's how many people were accepted. Maybe you were here. And they're saying, you were good enough, but maybe you were good enough last year. And in my daughter's case, they said, consider applying again next year. That's what they actually told her. She didn't. She only applied because I wanted her to apply there. She wasn't really that interested in going. Another $75 down the drain, right? Every time you apply somewhere. But the thing is things of this nature, you're good enough to get in, doesn't mean you're going to get in. But the fact is there is a line in the sand. There always has to be a line in the sand. It can't be random because it would be too difficult for the college admissions to try to figure out, you know. So they already have the numbers and they're saying, okay, you know, this person reached it, this person reached it, now we'll go to round 2. Now that's where all your extracurriculars and things like that can really be useful, okay? Does everybody understand that? So SATs are a great example of something like this. Any questions? We're going to move on to something else, okay? Now, before we move on to the next thing, I want to talk about, I call them the magic numbers. If you have your formula sheet, does anybody have their formulas with them? On the formula sheet, I have these on there. There's 4, I call them magic numbers. They're the 4 most commonly used z-scores because of what they represent. A lot of times, we're interested not in the high end or the low end, we're interested in maybe a range of values. And what I mean by a range of values is we know that the extremes are unlikely. All right, that's what we call them outliers. Extremes are not very likely, because if extremes were likely, then you would all be over 7 feet tall or under 4 feet tall or something, right? But there's no extremes in this room in terms of height or in terms of age. I don't think there's anybody who's 100 years old in here, right? We're all pretty generic in here, right in the middle. But if I said, I want to capture 95% of all the scores. Let's start with this. I want to, of whatever we're measuring, assuming it's a normally distributed set of values, I want to capture 95% of them. And the reason you do this, okay, is because you can't capture 100%. If I said I want to capture 95% of Americans, whether it be by height or by age or whatever it is, I don't need 100% because that gives me too many extremes. I want the bulk of the group, and I'd like to know what am I looking at if I'm looking at the bulk of the group. So if 95% is there, or in other words, probability of 0.9500, then what is in each tail?
2.5.
2.5% exactly, or 0.0250. I'll write it like that, because we have to look up something in the table. And how about over here? 0.0250. I would like to know what is the z value that I'm going to look up. And here's the cool thing. Because of symmetry, whatever this z value is here, this will be the negative value. Right? Last day we looked up between -1 and 1. We looked up between -2 and 2. Wait a minute. When we looked up between -2 and 2, do you remember that number was just a little more than 0.95? We looked that one up last day in your notes. So, so what number am I looking up? What probability am I looking up? Well, if I want 2.5% in this tail, then doesn't that mean that I want 0.9750 to the left of that? What z-score would this be? I'm going to show you the notation that's universally used. Now this is your favorite one because this is the only one that has exactly that value in the table.
1.96.
1.96. Which, by the way, is by far the most commonly used z-value for future reference. 1.96 would be the z-value. And we write it this way. What z-value would correspond to a 2.5% tail? We write it z with a subscript of 0.25. We write it as a subscript because we're saying this is a constant. This is not something we're going to calculate. This is something we're going to use or look up. The z that corresponds with this tail is 1.96. So if I wanted to capture 95% of all outcomes, we could write it this way. The probability of being between negative 1.96 and positive 1.96 is 0.9500. That's what we just did. We're working backwards now. We call that the magic number because in most instances, we're going to be doing this later. It's called hypothesis testing. I am trying to determine the effectiveness, let's say, of a new pharmaceutical drug. Or I'm trying to determine if somebody's claim is valid or invalid, maybe in advertising or something. I can't look at 100% of all possibilities because that allows extremes into the game. No. So I said, if we consider 95% of all outcomes, we'll exclude the outliers. Then I'm looking at anything between negative 196 and positive 196 as a z-value. And that will help me make my conclusion a lot easier. Because again, it can't be everything. I'm going to give you a simple example. We want to design, let's say, a Mesa sweatshirt. And we really want people to wear it. But we don't have the ability to come up with, small, extra small, medium, large, extra large, behemoth. We don't have the ability to have a million ranges. So what we're going to do is we're going to make one size. Now, is it possible that one size would fit all Mesa students? No. But would there be a size, a perfect size that the vast majority of Mesa students could fit into? Yes. Who would we be excluding automatically? The outliers, the extremes, the super giants or the super small. But we'd be capturing the vast majority. Does that make sense? For a big person, it might be a little snug, and for a little person, it might be a little loose, but they could still wear it. We could come up with one size that maximized the number of people that could wear it. That's what we're talking about here. Outliers aren't bad, but there's nothing you can do that will always include everything. It doesn't work that way. Anybody here ever work at a restaurant? I'm going to give you a simple example. Okay, I go out to eat often. My brother and my father and I go out every Friday. We take my dad out to lunch. And we have a rotation of places we go to. They're all really good. But I noticed something about all of them. They serve really large quantities of food. And one of them, the owner's a good friend of my brother's, and I asked, why so much? Not that I'm complaining, but why so much food? I'm guessing you guys throw a lot away because people don't always finish. Because yeah, we do notice that. But this is what we wanted to do. Now think about that for a moment. You're at a restaurant, portions. Who decided what the portion would be? Let's say you're going to buy, a slice of lasagna, or maybe you're going to get a steak. Whatever you're getting, it can be huge portions, it could be small. How do we decide on the portion? So some of you folks will go in there and go, I have to order 2 meals. There's just not enough food for me. And others would say, I can never finish anything. It's way too much. Would you agree that it would make sense if you own the restaurant to choose a portion that the majority of the people would be content with? I had a football player in my class last semester, and he was about 300 pounds, and we joked about it because he ate 2 lunches every day. He was talking about, he'd be shrinking before our eyes if he wasn't eating every, half hour. But that person is not going to be content at any restaurant, is it? Because huge appetite. But then you have the really small petite person there's no way they could ever eat that much food. Restaurants aren't designed for those folks. They're designed for the masses. So the portion size would always have to be something kind of in the middle. But we kind of need to know where the middle is. Does that make sense? So if I'm a restaurant, I want to choose a portion that the vast majority of the people would be content with. If you left saying that just wasn't enough every time you went, that's a problem. If you went every time, God, I can never finish. Maybe I'll just take it home. But in general, if most of the people are content with that size, you'd say that's a good size. That's why we say we're not interested in capturing 100%. Now, what if I really want to catch more? If we're doing certain types of studies, for example, we're doing cancer studies, maybe I want to include even more. I want to make sure that I capture even a higher percentage of people to make sure I don't miss anything. Let's change the 95 to 99. And we're going to come up with the next magic number. If I change that to 99, a little bit higher here. The next one I'm going to look up is 0, 0.05. If I have 99% in the bulk, then how much is in each tail? Well, it'd be 1% total, so it'd be 0.5% in each tail. Does that make sense to everybody? So this would be 0.005. And I'm putting the fourth decimal place to remind us that that's what would always look like. So I need the z-score, but if I have 0.5% in this tail, then how much is to the left? 9950. Everybody cool with that? 9950. So now let's look that one up. What is the closest z-value to 9950? Where is it? 99. Oh, this is kind of interesting. Look at your table. It's got a little asterisk and an arrow. Do you find that interesting? The author's telling you, it's right here, folks. It's right here. It's between two z-scores. Okay, it's right there. It's between two z-scores. What two z-scores is it between? Can you tell me?
2.57 and 2.58.
Beautiful. And it turns out there is a number we use. It's between 2.57 and 2.58. Remember, the numbers are all computer generated. So this is one of the times we actually go to a third decimal place. And all the books will have the same number in them. And our book has this, it has it in a different place. So the z-value we use is 2.576. Strangely, it's not 5, because it's not exactly halfway. This is a computer-generated value. Now, if you use 257 or 258, is it going to make a big difference in the long run? No, but if something's a close call, and what I mean by a close call is we're testing a drug to see its effectiveness and it's right on the edge of acceptance or rejectance, we need as much accuracy as we possibly can because we need to make the right decision. This happens in real life all the time. There are things out there that did not get approved by the FDA because they were too close of a call. They didn't make the cut. They might have been great, but they didn't make the cut. Whatever we said was the line in the sand, they might have come really close. So we want to get it right. Later on, when we start doing this hypothesis testing I talked about, it's literally like a court of law. Guilty or not guilty, right? And therefore, what's the line in the sand that helps us make this decision? It's always based on a calculation, not based on opinion. So that's the thing. If we base it on opinion, then we could have different results. But if we base it on the information, the data, the calculation, then everybody comes to the same conclusion. That's important. So this is my next line in the sand. It's the z-score that corresponds with a 0.5% tail. So if I want to do this, so now let me write it. The next one. And again, these are in your formula sheets. So if I said 576, I've captured 99% of all conceivable outcomes if I fall between those two z-scores. Okay, that's kind of cool. Now, let me do a new what if. What if I don't want to go in both directions? What if I only want the top 1%? I don't want to exclude the outliers. I only want the top 1%. Or I only want the top. We just figured out what the top 10% was, right? That was the z-score of 1.28. What if I want the top 1%? I want this z-score right here that corresponds to the top 1%. I don't care about the bottom 1%. I only care about the top 1%. So what's to the left of this thing?
0.99.
0.99. So let's go back to the table. What z-score is the closest to 0.99? 0.990. You're right about here. Do you see a probability of 9898 and a probability of 9901? Does everyone agree that I got to be in? So what two z values are those?
2.32 and 2.33.
Do you have the tables?
No, I left that.
Oh, I've got extra ones up there, yeah. You kind of need these. Unless you can see this from where you're sitting, I don't think you can see that. I can't see this from up here, so I doubt any of you. Can any of you actually see this? Yeah, I'm putting this up here because this is what you have in front of you, but don't try to read this from where you're sitting. Look at your table. That's if you could read this, you've passed the eye test, you know, infinitely well. So it's between 232 and 233. Well, it turns out it's another 3 decimal placer. This is the only one, by the way, that's only 2 decimals. So the z-score that corresponds with exactly a 1% tail, and we write it this way, is 2.326 again. Again, it's computer generated. The computer just, if you had powerful computer software, statistical software, you could do these. But it's easier just to have them written down. So on your formula sheet, I have these. Now, what's the only other important number, do you think? Top 1%? Well, just a minute ago, we did the bulk of 95% and the bulk of 99%. Now we said the top 1%, so what do you think goes right along with that? The top 5%. And that's the last of we call the magic numbers. And what I mean by the magic numbers is, in reality, these are the only numbers that are really ever used to do something. If I said, what's the probability of something happening, you have to calculate the z-score and look it up. But ahead of time, I say, no, I want the top 5%, or I want the top 1%, or I want the people in this range. Oh, that's a preset value. That's a constant. I don't have to calculate that. I just look that up. Big difference. Okay? So the one that corresponds with 5% means that this is now 9500. I'll put it up here. Now, I need the number that's the closest to 9500. Oh, what do you know? They got the arrow and the asterisk again. But they're telling you, yeah, folks, it's right here. Look, look. That makes it a lot easier, doesn't it? This one actually is exactly halfway between. So this one is 1.645. You say, how does Mr. Brown know all these? Because these are the only ones that are ever used, and I use these all the time. Do I want you to memorize these? No. I want you to have them in front of you. They're on your formula sheet. Who has the formula sheet with them? The actual formula sheet. Can you pull it out? No, not the tables, the formula sheet. The one I gave at the exam. If you have that, I want to show you where they're located so you don't have to keep writing them down and looking them up. So on your formula sheet, okay, on the second page, right in the middle, it says common z values. And then it says z with the subscript of 05, 025, 01, 005, exactly what we just did. And it gives these values. They are constants. You don't ever have to calculate these. You're going to use these. So if we work backwards and I said, what SATs correspond to the top 1%, the top 5%, the top 10%, the middle 95%? You can just use these numbers and the calculation is quite simple. Does that make sense? That's what we do in real life. If a situation occurs and I say, what is the probability of that situation happening? That's where you have to calculate the z-score. That's what we've been doing with SATs. But if I said, I want the top 5%, you have the z-score already, and then you work backwards.
Is this only if it's like a bell curve and it's only evenly distributed?
Yes.
So this doesn't work for everything.
This does not work for everything. It certainly doesn't work for income.
Correct.
Right? I use income because we know the curve is long and skewed. Anything that is normally distributed, or we say essentially normally distributed. Here's the problem. In real life, could you know if something's normally distributed? Human heights, for example, we consider as normally distributed based on past history. But maybe next generation they won't be. We don't know how tall everyone is next generation. But right now, we consider human heights to be an example of something that is a literally perfect normal distribution. Duration of pregnancies is another one. We consider literally perfect normal distribution. And I love using that one because a lot of folks don't realize that it's actually that simple. I became kind of an expert. I have a lot of kids, and we did all the reading and everything, and the way due dates are predicted. And I always laugh when I've had people tell me, well, most babies are late. No, not most babies are late. About how often? About half. The other half are early, but there's still some that are born exactly. I have many children. I only have one that wasn't born on the due date. It was a couple days late. My first three were all born on their due dates, which is really, that's like saying I flipped the coin 1,000 times and got exactly 500 tails each time. But it made it easier to predict. But the thing is, I say this jokingly, babies are never late. Babies are born exactly when they're supposed to be born. The prediction was incorrect. A lot of people don't think of it that way. Don't. Every doctor will tell you that. They're making a prediction. And do you know how they make the prediction? I find this really interesting because we consider this to be an absolute science and we have all the numbers and it's really easy to calculate. Do you know how they make the prediction? Because how long is a pregnancy? What is the number most human beings use for pregnancy?
I don't know.
It's in weeks. It's not in months ever.
36 weeks.
40 weeks is what most people use. A pregnancy is actually only 38 weeks. But why do they use 40 weeks? Does anybody know? Because between a woman's period, the highest probability to get pregnant, do you know when it is? Exactly halfway between. This is absolute science. The highest probability of getting pregnant is exactly halfway between. Halfway between is 2 weeks from. So what do? They go back to, they say, okay, when was your last period? And we're going to say, all right, you probably got pregnant in the middle, so we're going to go 40 weeks from your last period. Does that make sense? Oh, that's how they got the date. Now, does that mean they got pregnant exactly at that day halfway between? No, there's basically, 4 weeks they could have got pregnant. The highest probability was right in the middle. That doesn't mean that's when it happened. It's the highest probability. It's like flipping the coin 100 times. The highest probability is 50 tails, but it doesn't mean it's going to happen that way. So it's actually 38 weeks. And so Des is the only parent I think in here. So I'll tell you what happens. So you're several weeks in and you go to the OBGYN and they do the ultrasound thing, which is really kind of cool because you see the little baby kicking and doing all this stuff. And they say, okay, based on the size of things now, we're going to adjust the due date. This is what they always do. Our first due date was just a rough guess. Now that we see the size of the baby and things like that, we're going to adjust the due date maybe a few days in either direction. Now it's a more accurate prediction because now they're basing it on a little bit more fact. Does everybody understand? That's how. Now, can the baby still be late? Yes. Can the baby still be early? Yes. The standard deviation is about 7 days. What do we consider late? Does anybody know? 2 weeks. Anything past 2 weeks, we say the baby's late. What do we consider preemie? 2 weeks early or anything earlier. Does that make sense? Range rule of thumb? Almost all babies are born within 2 weeks of their due date, which is 2 standard deviations. It's like, does that feel like an oh-duh? That's a cool oh-duh. They go, oh, that makes perfect sense. Babies are generally born within 2 weeks either way because, again, it was a raw prediction. If it's more than 2 weeks early, we say they're a preemie. If it's more than 2 weeks late, we say they're late. That's it. But because of the bell-shaped curve. So going back to your question, if it's not the bell-shaped curve or if it's really not close to it, we do it a different way. We don't use the z-tables. There's another set of tables that we use that's going to come a little bit later. Okay, it's similar in the mathematics, but the z-tables are perfectly executed because of the perfect symmetry and the fact that we can calculate every single outcome, which is kind of cool. Okay, next example we're going to do. IQ. I like IQs because, like SATs, IQs are perfectly normally distributed because they are standardized once again. Okay? All human beings have an IQ. Do you know what IQ stands for?
Intelligence quotient.
Intelligence quotient. Good. Does an IQ measure how smart you are? This is tricky. Does an IQ measure how smart you are? No. Do you know that you can find the IQ of a child? You can measure a 4 or 5 year old's IQ. And then as they go through life, of course, their IQ is going to get higher and higher and higher, right? No. Short of a head trauma, your IQ cannot change. So does an IQ measure how intelligent you are if you can take a 4-year-old's IQ? No. It really measures the capacity of what you're capable of. Which is why doing it with a child is always kind of iffy at best. Because, They're answering questions. But your IQ really is about the capacity of what you can do. So a high IQ means you are capable of doing more than somebody with a low IQ. It doesn't mean you're smarter. If you're an adult, a high IQ probably means you're pretty smart. But a child can have a high IQ and they don't know anything yet. Does that make sense? So the IQ is this number that measures what you're capable of. And there's a lot of controversy over the years. How many of it, be honest, how many have done an online IQ test, right? You're on the internet and it says take the IQ test, you do it, you answer all the questions. You guys ever do those? I'll do them occasionally. And every time I get them all right and it says my IQ is over 200 and all that stuff. By the way, it's not possible to have an IQ over 200. It's not possible. I did read just a few weeks ago that some kid, they'd measured the highest IQ ever. It was higher than Stephen Hawking and Albert Einstein, some kid. And it's like, sure he is. Because the person doing it, apparently it was a family friend and all that, sounded a little bit sketchy. But an IQ, if done right, an IQ is a number and a perfectly bell-shaped curve. The mean is exactly 100. So the mean of all human beings on planet Earth is an IQ of 100, and the standard deviation is exactly 15. Like an SAT, it is standardized to make the numbers easier to calculate. Okay? Now, with that said, an individual selected at random, we're always starting with selected at random. We're not going to say, oh, let's take the smartest person we know. No. An individual selected at random, let's find the probability of an IQ higher than, let's say, 106. 106 above average. What's the probability that somebody has an IQ higher than that? So the question is, the probability that a value is bigger than 106, I need to convert 106 to a z-score. Is that a hard calculation? No, it's an easy calculation because we have the mean and the standard deviation right in front of us. So if we do it this way, it's z is bigger than what? 106 minus 100 over 15. Now, by the way, this is not always going to come out as a perfect terminating decimal. Most of the time when you calculate your z-score, you're going to have something you have to round off. Okay, everybody got that? Most of the time. How many decimal places do you round it to? What do you think? 2. 2, because the table has 2. Could I go more than 2? Sure, but the third decimal won't help me look it up. There's not, by the way, you could go 10 decimals if you want. But if we're actually going to look it up, the table's only got 2, so you only need to go 2. Okay, so what is this? This is the probability that z is bigger than what?
0.4.
0.4. Now, I'm asking, again, I always like the picture. I'm asking for a number that's above average or higher. Is this going to be more or less than 0.5? Less. Because I'm already on the right side and I'm asking you for even higher. That means that I'm going to have to subtract. Okay? Because I have to look up that number. So, let's find that number. The probability that z is smaller than 0.4 is what? 0.6554, so the answer would be 3446. That's a little more than a third. Would you agree? A little more than a third of people have an IQ above 106. That's an easy way to think about that. 106 is above average, but it's not, incredible. Now, mental retardation. Somebody who's mentally retarded means their brain is not going to fully develop like somebody who isn't. There's actually a definition, and it's based on IQ. Does anybody want to venture what is the definition of mental retardation? It's an IQ below
0.8.
Exactly right. And what's 2 standard deviations below? You're exactly right. So what IQ would be exactly 2 standard deviations below? 70.
Oh,
Mental retardation is defined to be anything below 70.
oh, okay, times 2, okay.
2 standard deviations. Forrest Gump. I just remember, how many have seen Forrest Gump? If you haven't, oh my gosh, one of the greatest movies ever made. Forrest Gump was not the sharpest tool in the shed. Forrest Gump, his mama had to pull some strings to get him into public school. His IQ, do you guys remember in the movie? His IQ is supposed to be about 75. So he's really close to the line. He's barely got a brain going on there. He just was right place at the right time his whole life. But not, you know, not the sharpest tool in the shed, right? Life is like a box of chocolates, remember the whole line. But I always use that example because people say, well, was Forrest Gump retarded? No, Forrest Gump was not mentally retarded. He was above the line in the sand, but not by a lot. So that's the definition of mental retardation. Now, what if somebody's exactly 70? Then we say things like they are mildly. What if somebody's IQ was like 50? You know, what if it was really, really low? Then we'd say it's severe. We actually put adjectives in front. Because if you're right at the borderline, you may still be able to function, you know, in society. Going to 4-year school, I don't know. You know, I don't know if that's something that's in the works. Now, flip side is high IQ. High IQ. Does anybody know what we would consider a high IQ? And we don't go with the exact same rule of like 2 standard deviations. It's usually we go with a percent. Top 2%. Now again, I wasn't there when this was decided. There's an IQ that would be the top 2% of IQs. Let's work backwards and figure out what it is, because we have the ability. Okay? I want the IQ that corresponds to extreme tail probability. I want 0.02 in the tail. So what z-score would I be looking up? Well, the z-score that corresponds with the z-score that is closest to having 98% of the values to the left. So what z-score would that be? What z-score is closest? Well, it looks like it's between 205 and 206. Do you agree? So just for, let's go halfway between. IQs are always integer values, by the way. So we're just going to round whatever we get anyway to the nearest integer. So what z-score do we want to use? 2.05. Let's use 2.055 just to be safe. So what is the IQ? Remember, we just did this a moment ago. X would be mu plus sigma times z. Okay, that's always true. The value is always equal to the mean plus the number of standard deviations above or below. So in this case, that would be what? 100 plus 2.055 times 15. To the nearest integer, what is this value? And the reason I'm saying to the nearest integer is IQs are never reported as decimal values. They're always integer values.
31?
You got confirmation?
31?
31?
131?
Wow, okay. 31 is kind of mild. Yeah, I think you're right. I think 130. So 131? So if you have an IQ that has been measured and reported, and by the way, public schools used to do this. They used to actually measure kids' IQs when they were young. I had mine when I was like 4 years old. They did this. They will measure, not everybody, but if they think somebody is, you know, a little bit off the, the mainstream, high or low, they used to be able to do this. Okay? Somebody has an IQ that's been measured at over 131. They're usually going to get invited to join an organization. Does anybody know what that organization is called? Mensa. Mensa is an organization of high IQs. How many have heard of Mensa?
I've heard of the term Mensa.
That's what Mensa refers to. I don't know if it's an acronym, like you can probably look it up, or if it's a name of somebody. But Mensa, I don't know that I want to belong in that group. What is the Mark Twain expression? I don't want to join any organization that would have me as a member. I don't know that I'd want to hang out with people who believe they're smarter than everybody else. What do you talk about? Well, obviously you talk about everybody else. I just find that to be kind of funny, but there's actually an organization, high IQ, and there's a number, there's a line in the sand that is measured the way we just did it. Isn't that interesting? I can still remember I was teaching a class a few years back, I think it was a stats class, and I had a student early on in the class, he told us, he stood up and told us he was super high IQ. He told us his IQ was around 200. He was serious, he wasn't joking. And he says, you know, I am smarter than anybody you're ever going to run across in your entire life. He was telling us this. He hopelessly failed the class. I mean, he couldn't do anything. Probably one of the worst students I've ever seen in my life. And I've taught 40,000 students. But he started by telling everybody how smart he was. And I'm so much smarter than the rest of you. I can't add with a calculator, but I'm so much smarter. Why he told us this, I don't know. And when he came up with the IQ of around 200, I just had some fun and looked it up online. And there have been very few human beings who've ever had their IQ, I believe 160. It was like the highest ever measured kind of thing. So obviously he was just full of it. But I'm smarter than all of you because my IQ is so high. Well, that's the thing. High IQ doesn't translate to intelligence. It translates to capacity and capability.
The irony is that Mensa or Menso is a slang term in Spanish, which means you idiot.
That's funny. Yeah, I don't know if it's an acronym or not because I don't care enough to. But I wanted to throw that out there because everybody understands IQ. They know there's a number out there, and if 100 is average and your IQ is above 100, that means you are above average. But does it really mean anything? I think if I took the top students in all of my classes, I would tend to think their IQs are probably high. But I don't know that the highest IQ in any of my classes is the top student. I don't know if the top student is the highest IQ. I would think that there's a correlation. I would think that the people that perform the best often have higher IQs because they're capable of more, but sometimes people just work really hard. They have great work habits. I've dealt with a lot of very, very smart people. I taught many, many, many years ago. I taught a private school, you know, the private wealthy kids school, and I taught all the honors courses. I loved it because I wanted to teach the kids who really had something going. But I had kids who were really, really smart and didn't graduate from high school. The parents were wealthy, the kids were really smart, and they dropped out of school. They just didn't care enough. So in other words, just simply being smart or having high IQ doesn't mean you have a free ride because if you don't have any work habits. Anybody here ever play a sport? High school, college, play sport. Most of you probably play a sport. Did you ever work with people who were really special, real talented? You know, you had people on your teams maybe that were really talented. Did they always go far? Or did sometimes they don't do anything? Because they were really talented, but as you went farther along, if they didn't have the work habits, you know, they kind of fell by the wayside. And sometimes it wasn't the most talented people that made it, it was the people that worked hard. They had some talent, but they worked harder. So I like IQ as a perfect example of something that in the long run doesn't really mean a whole lot, but it's a good thing to measure. So now, let's do a few calculations involving this. All right, you're going to grab an individual at random, and I want to find the probability of an IQ, this time we'll do a between 91 and 105. I'm going to grab an individual at random, and I'd like to know what is the probability their IQ is between 91 and 105. So the question is, what's the 91 is less than my x is less than 105. This is not the z value. You can't get z's of 91 and 105. But that's the way the question is looking. What's the probability that the value I'm looking at is between 91 and 105? So obviously we need to convert this to z-scores. So the way I convert to z-scores, put z in the middle now, right? And then calculate the z. So this would be 91 minus 100 over 15. This would be 105 minus 100 over 15. Now these are not going to come out as terminating decimals. So you're going to have to round these because they're infinite decimals. And you can't really look up infinite decimals. That's not really efficient. Well, actually, the first one will. It's the second one that won't. Okay? So this would be the probability that z is between what and what? What's the first one?
Negative 0.6.
Negative 0.6. I'll put 0.60 because remember, we need that second decimal place because the table has 10 values because it always has 2 decimal places. And what's the second one?
0.33.
Yeah, you have to go with 0.33 because 3333333 is not going to be on the table. Okay? All of the calculation of the problem is basically this. That's all of the math. The rest is looking it up. All right, so that means I want the probability of the bigger one minus the probability of the smaller one. And notice that my inequalities have to be going in the correct direction. You cannot look up a greater than. You can only look up a less than. Because the table, look at the picture. I mean, this is how it always is. You always look up to the left. So if I want a betweener, this is a betweener. Okay? This is what we just calculated. That's 0, that's negative 0.6, that's 0.33. I want the area between. That's why I take that one, and I subtract that one, and that gives me the between. So you always take the bigger one minus the smaller one. It's the same every time. So, 0.33, what do you see?
0.6293.
6293, and negative 0.60.
2743.
And that value would be what?
0.355.
Keep going. 3550.
Yeah.
So a little more than a third of all people are in that range of values. Is this hard to do, what we're doing? No, not really, not at all. Now, I've chosen 2 particular examples, SATs, because everybody understands that, most of you have taken an SAT, you kind of understand their scores, what do they mean? Okay, they took my score and they converted it to this big number, but I can convert it back to a z-score easily. Same thing with IQ. But these numbers are so nice. It doesn't always work that way, though. Let's take something where the numbers aren't so nice. Okay? This is an example I remember when I was in school that they used. And this was actually a reasonable example. I'm just making up the numbers though, all right? This is kind of funny. They used this when I was in school. There were actually typing schools. There were places you actually went. Now, I was fortunate. I took typing when I was in high school. The basketball coach, who was also like a business teacher, was the typing instructor. And I learned to type in 9th or 10th grade, I can't remember. But I learned to type. I mean, you learn the keyboard. And I could type 100 words a minute in high school. I can type 100 words a minute. The problem is I make lots of mistakes, so the most important key for me is the backspace. But back then there was no backspace key. You made an error, you made an error. They invented that some years later. So typewriters, people learned to type. There were actually places, you wanted a job, let's say you wanted a secretarial position, or you were a bookkeeper or something, you had to learn how to type. And they didn't always teach that in school when you're growing up. So you're an adult and you wanted to learn to type. You actually went to a typing school. It sounds kind of funny now, You know, in fact, I have family members, they don't even type when they text, they talk to their phone, and the phone texts for them. Of course, it misspells about every third or fourth word, which I think is really funny. Yeah, so I'll be reading text from my brother going, I don't understand what that means. Orangutan for lunch. You know, it's just something goofy. Okay, at a typing school, the speeds, and this is reasonable. This is something they used to use, these stats. The speeds are normally distributed. This is important. With a mean of, I'm just going to make it up now, of 80.6 words per minute. That's how you're measured in typing, by the way. And a standard deviation of 12.65 words per minute. Okay, this would be more reasonable numbers now. The key is that the speeds are normally distributed, and in reality, saying they're normally or essentially normal is close enough. They don't have to be an absolute perfect. They have to be essentially normally distributed. Okay? Now, this typing school has been around for a long time. They've had maybe thousands of people go through. And it's only this typing school that we're talking about. We're not talking about all human beings and this is a sample of human beings. No, this would be a population. Everybody that's ever gone through this school, this would represent the population because we're only looking at this school. Has everybody got that? So in this case, we can treat it as a population. SATs, we treat as a population. Because in SAT, the score you get is not measured towards all SATs ever taken. No, it's only measured on that SAT. So if 1 million high schoolers are taking the SAT this Saturday, your score is measured against only those people taking the SAT, not the kids who took it last year. Do you know why it's not measured against last year's kids? It's actually a really simple reason. Different test. Never used the same test twice in a row, so how could you possibly measure today's test versus last year's test? You could make an argument, maybe last year's test was easier, maybe it was harder. They're similar tests, but they're not going to be identical tests. Oh, that's why you can't, you got to take everybody that year, okay? You led the league in scoring this year. The person who led the league in scoring last year scored more points. So does that mean you no longer led the league this year because last year's person scored more? No. You're talking about this year, not last year. So it's just that situation. Find the probability an individual types slower than 100 words per minute. We'll do a few of these. So in picture form, if the mean is 80.6, I'm asking the probability somebody scores slower than 100, more or less than 0.5. More or less than 0.5. More. Why? Because I'm taking a value that's way above average and asking what's the probability of being less. Aren't most people going to be way... Remember, half the people are going to be below average. This is way above average, and I'm asking the probability of being smaller. Okay? So, the probability that your value is less than 100 is equal to the probability that your z-score is less than 100 minus 80.6 over 12.65. And again, like before, 2 decimal places is all I need. So we've got a z-score of 1.53. Oops. Probability of p. No. Probability that z is smaller than. Now, can I look this up or do I have to tweak it? Can I just look this up directly? Yeah, because I'm saying less than this value. I don't have to subtract, I don't have to do anything. So, on the table. What is the probability of a z-score that is less than 1.53? What do we get?
0.9357.
9357? You all agree with that? So at our particular typing school, almost everybody types slower than 100. By the way, if I said, well, then who types faster than 100? What would you do? You subtract that number from 1. Exactly. Would that be a hard question? No. But it does matter which way the inequality is falling.
So I'm looking at 0.93704.
153, well, let's look at it. 153, oh, you're right. You're right. We were off by 1 column. Good call. 9370 is correct. Yeah, we somehow got off by 1 column. I think what some of you do is you go like this. 1, 2, 3. But remember the first column is the zeros. The last column is the 9. So yeah, that's good catch. Good catch. All right, let's do a similar problem. I want to grab a former student at random. I'm just looking in the records and saying, now what's the probability? Find the probability that a student selected at random, and I'll always use those words, a student selected at random is between, let's say, 75 and 95 words per minute. Okay? Well, since the average is a little more than 80, I'm looking at a value below average and a value above average. Okay? So we're looking at something like this. All right, so let's do this. It's very important that we state the problem correctly. Don't calculate the z first. State the inequality. I'm looking for an x that is between 75 and 95. Now, I can't look that number. I need to convert it to a z, but I want to express it correctly. So that means I'm looking now for a z between two numbers. So the easiest way is just to do the z right here. So 80.6, 12.65 is smaller than z is smaller than 80.6. These are inequalities. They're not equals. Now I need a calculator. I can't do this part without a calculator. So what do you get from the first one?
Negative 0.44.
Negative 0.44. And let's do the second one. Two decimals, what is the second z-score?
1.13.
Careful.
Uh-oh.
To 2,
Oh.
it's
1.14.
138, so we're going to use 1.14. That's why I said make sure you're... By the way, will it make a difference if I'm off by a little? Yeah, it actually will. This number was a little bit off because we were one column over. We'd be talking about the exact same mistake here. We'd be one column over, so we would be a little bit off. Would it be an outrageous error? No, but it's like getting incorrect change at the check stand. You know, it's still an error, and we don't want to make an error. We don't like errors. We still love people who make errors. We just don't hang out with them. You know. So it's a betweener, so that means I take the bigger one and I subtract the smaller one. Okay, so the probability that z is smaller than 1.14 is what number? 8729. And the probability that z is smaller than negative 0.44, 3300. And that gives us what? 5429. So a little more than half. And there should be absolutely no difficulty in the calculations because all you're doing is calculating a z-score. You're finding the value of a quotient. That's not challenging in general. You just have to be careful. So this is the question. This is the algebra to convert it to a z. You notice that this is x, this is z. X and z are not the same, well, ever. That would be impossible. That'd be like saying, let me take your height. Your height is equal to your z-score. Well, if you're below average height, then that means your height is negative? That doesn't make any sense. No, your height is your x value. Your z is where you stand relative to everyone else. So the inequality involving the value and the inequality involving the z are always completely different, but I need to convert it to z so I have something to actually look up. You can't look up the score. So it's kind of like this. Let's say you were involved in a really large scale test. Maybe you're a UCSD student and there's 400 people in your class, but you were involved in a really large scale test and you have your score. Well, what's the first thing everybody wants to know? How did I do? But more than how did I do? How did I do? What do you think?
Compared to everyone else.
Compared to everyone else, yeah. Did I do well? Did I do poorly compared to everybody else? Because the number that I get doesn't really mean anything to me. I don't know how to do anything with that. But how did I do relative to everyone else? So that's why it's the z-score. The z-score is the number that tells you how you did relative to everyone else. If it's positive z-score, you were above average. If it's negative, you were below average. If it's like more than 1 or even 2, then you're really far above average. That's why it's important. Then you can say, well, what was the probability of somebody scoring higher than you? Well, then just take your z-score and we look it up. But we have to start with your individual score and then convert it to a z-score. Does that work in just a regular classroom situation? Does that work the same way with probabilities and z-scores and stuff? Go back to what Dylan said. It only works if you have a normally distributed set of values. Do you think your test scores in a classroom situation are ever normally distributed? No, they're always skewed. Why? Because the bulk of the scores are at the high end, and so a low score. That's why a mean in a classroom situation is usually kind of meaningless. That's why you usually use the median. Because the mean takes into account the lowest scores, but the median is still the middle score. Income. We don't do the mean, otherwise the Elon Musks and Bill Gates of the world make the average American look very wealthy. Now, I have an interesting situation with that. Many, many years ago, before any of you were born, probably, okay, when Jimmy Carter was president, the American embassy in Tehran was taken over. They've made movies about it. It lasted a couple of years. It cost him his presidency because he kind of sat on his hands and didn't do anything for the longest time. And then Ronald Reagan got elected, and they released our hostages almost immediately because they knew Reagan would go in there and beat him up, kind of thing. But in the meantime, there was a lot of anti-Arab sentiment in the United States because that was also right after the first and second oil embargoes. 1973, 1977, Americans had set up most of the refineries in the other countries, and then we just completely took advantage of them. Basically, we were getting all this oil for dirt cheap and all this. And in 73, OPEC formed, the Organization of Petroleum Exporting Countries, and they got together and said, you know what? We're getting reamed here. Why don't we raise the price? And they did. And all of a sudden, for the first time, I mean, gas, was under 20 cents a gallon and everywhere in the U.S. for up until that point. And then all of a sudden, it went up to like 60 or 70 cents a gallon. And then in 77, they did it again, and now it went up to like $1 a gallon. Can you imagine gas being that expensive? $1 a gallon. Well, because of what was going on, the U.S. government decided we're going to try to get the government did this, believe it or not, some anti-Arab sentiment in the United States. So they started reporting statistics about some of the countries. And for some reason, they used Kuwait, which was actually one of our friends. They've always been a friend of the United States. And they reported Kuwait's average income, and this is 1977. I remember this because when I had stats. Kuwait's average income in 1977 was like $40,000. That's every person in the entire country. By today's standards, that'd be like $150,000. That's every person. And America's like, they're just killing us. What they didn't mention was Kuwait had the highest percentage of oil sheikhs of any of the Arab countries. An oil sheikh was the billionaires. Most of the country was in poverty. But they reported the mean income of the country to make people really angry and resentful because they were talking about perhaps even going to war to take back over the refineries. It didn't happen. But they reported the mean, and I remember because when I had statistics, we talked about this, saying this is why it's so dangerous sometimes if you don't have enough information. If you just go by the reported numbers, you never use mean with income. Did you know that, and I remember reading this when I first came to San Diego, the mean income in Tijuana is more than San Diego. Did you know that? Because of the sheer number of extreme wealthy people in Tijuana. It's unbelievable how many. I taught at a private school. We had one kid live in Tijuana, and his parents were billionaires. They owned land. He came to school in an armored car every day with security, which was kind of creepy at a high school. The kid, the black limo with the tinted windows, and he'd get out and you'd see the guys. Yeah, that was a great kid though, really nice kid. But his parents were billionaires. They owned a significant portion of Tijuana. The point being, if you report the mean income, it's kind of deceiving because we know Tijuana is not a wealthy area. There's a lot of poverty. But because some of the wealth is so extreme, it makes the mean. That's why this does not work. In that situation, it's not normally distributed. You can't use this to do anything that's not normally distributed. Because otherwise, see, the wealthy are going to be 20 or 30 standard deviations above the mean, perhaps. Which in this situation is impossible. I mean, being beyond 3.5 is almost impossible if it's normally distributed. Right? That's why we talk about, almost everything's between -3 and 3, and the vast majority is still between -2 and 2. But again, it's only if it's normally distributed. We're going to talk about what do you do when it's not normally distributed, because we're going to be doing that fairly soon. Okay? Everybody cool with that? All right, we'll take a break. We'll do some practice. Hopefully this stuff is not going to challenge you too much.